Great to be here. So this is joint work with a fantastic team, Yuanji Li, Yingyu Liang, Tengyu Ma, and Andrei Ristevsky. And let me start by giving a little bit of context. So I've had a little bit of a personal change of course. Maybe many of you know me more for my work on hardness, computational hardness. And in the last few years, I've become very interested in the opposite phenomenon, that problems seem to be a lot easier than we thought. So yeah, the motivating question is, is NP hardness, or in general computational hardness, an obstacle for understanding reality? So I'm not talking about the mathematical theory, which is very well developed and beautiful, but in terms of the application to reality. So, computer science has this, theoretical computer science is sort of somewhere between math and reality, right? So, so in that sense, in terms of understanding reality, so let me illustrate it with actually something I've worked on, but okay, so say you want to understand some piece of reality like the New York Times corpus of articles. So it's completely unsupervised, somebody gives the machine the corpus of articles, and then the machine is trying to understand, there's things like, a few hundred topics, politics, sports, weather, etc., and different articles correspond to this mix of topics, for instance. So that's called, so you want to understand reality in that sense, and so let's denote it by conceptually some point that you want to understand. And then what do we do? So mathematically, we draw a circle around it, right? We formalize a mathematical problem which says, here's my input, which is this matrix, what's the matrix, like the words that appear in the articles or something. So there's a mathematical formalization of the problem. And in this case, yeah, the problem is called learning topic model, something I've worked on, but it's existed for almost 2 decades. And then in this larger circle, this mathematical formalization, some clever people will come up and say, okay, this formalization captures NP-complete or NP-hard instances, namely instances that can encode SAT. Okay, this result actually is from some appendix of one of our papers. And so then we say, okay, now this problem is hard, right? But then there's this possibility, and we've always known this. I'm not saying anything profound. There's this possibility that maybe you drew the circle too big, and maybe there was a smaller circle which you could have drawn around the instances that you were interested in, which is tractable. And in fact, that is the case for topic modeling. We define something called separable topic models, which turns out to be a good fit to reality. And that's to check that, you have to actually run it on reality and see whether the separability assumption that we had is valid or not for reality. But okay, turns out it is, and so that set is tractable, and so that you can solve very fast. Okay, and this is highly practical. There are subsequent papers. It's highly practical. Okay, so the point I want to make in this picture. So we've always known this. Again, anybody who knows NP completeness knows that's all that's proven, right? And the point I want to make about this is that this outer circle that we drew was a social construct. Okay, it depends upon who formulated the problem, who the advisor was, whether they had coffee that morning, all the usual human factors. And so this was arbitrary. Okay, and the NP hardness gives us this potentially an incorrect feeling that we understand the problem. Okay, and in theory we've advanced a lot, and we have a lot of instances. I've been associated with hardness approximation, where this is especially the case. You have some algorithm which is not particularly good, and in this larger circle you find with a lot of work, some instances which match, on which the algorithm is indeed that bad, and it's NP hard to do any better. And we say, I understand everything. And I'm suggesting that that's not the case. Okay, so ultimately we have to go back, if we want a theory that applies to reality, to actually check, did we miss out some easy putting some smaller circle around the things we were interested in, which is actually tractable. Okay, so the moment I sort of started realizing this, I realized that basically we have to revisit everything. Not everything. Okay, cryptography, I don't think I think that those crypto problems are still hard. But, in real life problems with not a lot of structure, it's not adversarial structure, I think many of these problems are easy. You all know about, deep nets. People are fitting huge deep nets, huge non-convex problem, and people can solve it on very large inputs. So I think there's a lot of stuff going on. This is sort of the gestalt of the times, and I think we have to figure out, how to draw these smaller circles. Okay, so this was a prelude to say, why I'm interested in these things. Okay, why the switch from hardness to easiness? And I think that is actually very important if you want to understand reality.
There could be another alternative goal, not to draw the small circle which will contain only easily solvable problems, but to decrease the fraction of hard cases in it. So that's an intermediate goal. While there could be some bad cases, hard cases in the big circle, you might want to purify it, to draw the smaller circle, which is not devoid of hard cases, but has a much lower probability. Is it something you consider or not?
So you could do average case complete, but I'm not even talking necessarily about average case here. I mean, that's one way to draw the smaller circle, and you could do that. Yeah, the hard instances are only a very low probability. The trouble with average case, and this is why there's always been this Bayesian versus non-Bayesian and all this kind of discussions, is that, reality is difficult to model exactly. But, separability is sort of not a very difficult assumption, and it seems that the real life instances, whatever they are, very complicated, lie inside there. Yeah, so yes, average case is indeed one of the ways you could do it, but not necessarily the only. Okay, and the reason for hope is that machine learning has lots of models for input structure, so there's a lot you can play with, there's code you can download, and you can actually see, what works, what doesn't work. Okay, and the stuff I'm going to talk about is like that, structure that we discovered by just playing around and thinking about it from first principles. Okay, so without further ado, so these are the takeaway lessons from the talk, that there's fascinating structure in the inputs out in the real world. It is leveraged in existing heuristics. You've all heard about this, but actually you can download the code and see it, and it works. And many of these heuristics seem to solve NP-hard or other seemingly computationally intractable problems. But I think probably what's going on is this smaller circle phenomenon. And I think theory can help give new insight and understanding into these. Okay, so I'm hoping more and more people will try to do this. Okay, so onward to the topic of the talk, which is word meanings. Okay, more generally semantics of language. And what does it even mean to test understanding? And of course, this, if you go all the way in it, is leading to questions like Turing test and all those deep questions. But we're just talking about word meanings, okay? Meanings of individual words. And what does it mean to test understanding? So one task that's used both for computers and also for people, kids who can't, so is solving analogies. So development psychologists give these tasks to kids, and if they can't solve analogies, then that's a red flag. Okay, so that's one way to test understanding. So solve the analogy man is to woman as king is to. You can think about knowledge base extension. Somebody gives you pairs of words like that: Japan, Tokyo, China, Beijing, Germany, Berlin. 3 examples. Everybody in this room can give 20 more, right, or 100 more. Can computers do that? Okay, so notice that these are problems of unsupervised learning. So if you're used to learning theory as it was defined in theory more than 3 decades ago, that was supervised setting. There's the computer is given examples of inputs and labels, and then has to label more inputs. This is unsupervised. Also, the topic modeling that I was talking about, unsupervised. So you're given data. The computer is given data, and it's not told how to solve analogies. Somehow it just figures it out. Okay, yeah.
Sanjeev, if I can solve this problem, then it's obviously not NP-complete, right?
Oh, sorry. The NP-complete thing was my prelude to why I'm doing this. Okay, because I know many people have asked me, what's going on, and so that was my mission statement. Okay, let's see where NP completeness comes in here. That doesn't play a big role in what I'm going to talk about. This is mostly talking about that there's structure in the input, which is interesting. And yes, and along the way, you'll see that there's a problem which seems NP, it is actually NP hard, but gets solved anyway easily. But that's not the main story here. Yeah. Sorry for not clarifying that. Okay? Yeah, the talk is about structure word meanings. Okay? NP hardness will play a small role, not a big role. Okay. So, how can a computer solve these things in an unsupervised way? So one tool that's very useful is word embeddings, which is useful for these and many other tasks, like machine translation, answering questions, image labeling, etc. And just in the last few years, there's been tremendous success empirically in many of these tasks. And all right, so how do you capture the meaning of a word? Okay, so simple test. Think of a word that co-occurs with cow, drink, babies, and calcium. Milk. Milk. Okay, so all I had to tell you was 4 words that it co-occurs with, and you knew milk, right? You knew the word. So this is an example of what's called the distributional hypothesis of meaning. This comes from linguistics by Harris and Firth, which says that the meaning of a word is determined by the words it co-occurs with. Okay, the distribution of other words around it in large text corpora. This doesn't capture all aspects of meaning, but you can go very far with this. That's a surprising discovery in the last 5 decades. Okay, so let's start with a very simple way to formalize this. So just write down that distribution. It's very large. Okay, there are n words in the dictionary, 100,000. For all those 100,000 words, so for the word W, you write for all other 100,000 words, the probability that those words occur within, say, a window of size 5 in the corpus. So take a large corpus like Wikipedia and compute this empirically. And this long vector of 100,000 dimensions is an embedding for the word, right? And just by this distributional hypothesis, it's capturing whatever meaning that word has.
It's the probabilities of co-occurring or just whether it ever co-occurs? It's the probability?
Probabilities, yeah, the counts, yeah. Well, you see here, I mean, I'm leveraging that, right? These are sort of more frequent words that you'll see around milk. They might be things like other things, right? That Adi is drinking milk, but that's not a very common use of milk, yeah.
Just a technical question. Do they have to appear in the same sentence? Or
say distance 5. You know,
even
so
if they are...
the 5 is not important.
Even if they're separated by a period, yeah? If they don't belong to
that was not important, yeah. Okay? All right. So that's a very high dimensional word embedding. They are better embedding. So what people do in real life is they come up with dimension reduced version of this. So 100 dimensions, 200 dimensions instead of 100,000 dimensions. These are done by usually nonlinear techniques like singular value decomposition, which is polynomial time, but weighted SVD, which is actually NP hard. So that's the only place that NP hardness comes in. Energy-based models, which are non-convex, but people solve them anyway at very large scales. By the way, in theory, dimension reduction is synonymous with Johnson-Lindenstrauss. You do a calculation, and Johnson-Lindenstrauss doesn't explain any of this. You know, log n over epsilon square is too big.
Why?
Log n over epsilon square is too big. Okay. I mean, what's your epsilon? You know, and you do it. Yeah.
What's the advantage of SVD over Johnson-Lindenstrauss? Like taking the log n first?
Okay, so in general, so as I said, we've been playing around with data to see the structure and so on. So one empirical observation is that often in lots of crazy matrices you might define, you know, more crazy than this. You'll see on the next slide. Often the dimension, or the approximate rank of the matrix is like 20 or 30. So there's a lot of structure. Log n over epsilon squared will never be 10, yeah. I mean, yeah, somehow, yeah, log n over epsilon squared will never be less than a few hundred or 500,000. Okay, so that's, so I'll talk about more complicated properties of word embeddings or ways of doing word embeddings. But anyway, what are the other properties? So one is cosine similarity. So you take the cosine of the vector embeddings, and that cosine correlates with human ratings of similarity of the words. Okay, this has been long been known. The second is that analogies can be solved by linear algebra. This was presented in this paper by Mikolov et al., which made quite a splash in this area. So remember the analogy, man is to woman as king is to. So you take the vector for man and the vector for woman, take the difference. And now you take the vector for king and now you look for a word W such that this difference is as close to that difference as possible. So you're minimizing this linear algebraic expression. W is the word you're looking for. And out of the 100,000 words in the dictionary, lo and behold, the word that minimizes it is queen. Yeah?
Excluding king and woman.
Yeah, sure, yeah. Thank you. Okay.
Does it actually work for most analogies? I can think about cases in which men and women are very common words, but suppose that the wife of a king would be a very rare word, which...
Yeah. So the answer is, you know, the Mikolov et al. Thing, there's a simple analogy test where the success rate is something like 75–80%. Those are actually simple analogies. Then we took some analogies out of a book for English as a second language. These are sort of difficult analogies. You know, some of them are difficult for me. And there the success rate was like 25–30%. But that's not bad, right? Out of 100,000 words, you're getting the answer, correct answer with 25–30%. Okay, so all right. So what the open questions? So this is not the way. So this there's a lot of work here, especially in the last few years, and it's mostly empirical. So obviously, I'm interested in understanding what's going on theoretically. So question one: why do low-dimensional word embeddings exist? Okay, nobody seems to have asked this question. It's interesting. So. You know, there are all these methods. Let me tell you the simplest interesting method, which is from, which has been known for 25 years, but I got a pointer to it from the work of Levy and Goldberg. There's this PMI method, and PMI is the following count. So instead of the raw counts, right, co-occurrence probabilities, it's some kind of a non-linear measure of correlation. So forget the log. It's just if it's P W W prime, the probability that they co-occur close to each other, divided by the marginal probability, the product of the marginal probabilities. So that's like a correlation measure, right? The joint probability divided by the product of probabilities. Then take the log of that. So now take this matrix, 100,000 by 100,000, all the words in the dictionary, and the WW prime entry is the PMI value. Okay, it's some nonlinear thing for the, of the counts, right? Nonlinear function of the counts. So look at that matrix. If you just take a low rank approximation to that, say rank 300 approximation, then for each row now you have a 300-dimensional vector. Okay, that can be done by SVD. That already is a pretty decent word embedding. It's not the best, but it's pretty decent, turns out. I mean, Levy and Goldberg mentioned that. So, so the question is, what property of language causes this huge matrix to have such low approximate rank? Yeah?
So like each vector in this rank 300 thing would be a weighted combination of very important...
300 dimensions, yeah.
No, the first dimension would be a weighted combination of, you know, similarity to this sequence of words.
Oh, you're trying to understand...
Singular value, the vector corresponding to it would be a particular linear combination of very important words.
No, because there's non-linearity here, right? Each entry is, yeah, so it's not easy to interpret.
Each column is a word, each row is a word.
That's right, yeah. Oh, you're just saying, okay, so this is a 100,000 by 100,000 dimensional matrix. You take a 300 rank approximation. Now every row vector is a 300 rank vector. It's not important what singular value decomposition even is. Maybe that's what you're trying to figure out.
No. I'm saying the first vector in the SVD is a linear combination of the columns,
yes,
which means that it's a weighted some important words and less important
something like that.
words.
Something like that.
Okay. And then there's an
But-
orthogonal thing.
Yeah, but yeah, if you start thinking of it that way, it's very hard to see what the pattern is overall, like why this works. Yeah. Yeah. So again, yeah, you don't need to know what SVD is. Okay, it's just a rank 300 approximation. Okay. So so what property causes this? So just as an aside, if you replace this nonlinear thing PMI with just the co-occurrence counts, what I originally proposed, then the explanation why such matrices have low rank is something called topic models. Would say that there are like 300 topics, which I mentioned earlier, right? There are 300 topics, politics, etc. And then the document is generated in a linear way from those topics, and so that turns out implies that this matrix is low rank. But now we have this non-linearity going on, and still it's low rank. Yeah.
How much does this depend on the corpus from which you take?
It doesn't seem to depend so much. Yeah. I mean, if the corpus is big enough, right, you would imagine that sort of the innate meaning of the word sort of comes out. Something diverse like Wikipedia, which is all kinds of things. Indeed, yeah, if you take a corpus on chemistry, then obviously some words will have their chemistry meaning only in there. But something like Wikipedia will capture everything. Okay, so that was one question. Okay, why do low-dimensional word embeddings exist? Yeah, I mean, I asked an expert. I was sitting next to an expert at some occasion, and I asked this, and she said, what do you mean? You calculate the singular values, and they drop off after rank 300. And I said, yes, so why does that happen? And yeah, so people didn't seem to have asked that. Okay, so how do word embeddings reflect polysemy? That's the second question. Polysemy is a phenomenon whereby a word has multiple meanings. And for instance, the word tie can mean article of clothing or physical act, tie somebody. And you have one vector for this word, tie. How does it reflect the different meanings? So this has always been something that's bothered people in this field. Okay? So I'll give you a simple answer before the end of the talk. Third question, why do relationships correspond to directions? Okay, so this is a little bit misleading. This is a two-dimensional projection of this 300-dimensional picture. So these things are not exactly lines like that, but they still have fairly large inner products in 300-dimensional space. And there have been attempted explanations. There's this glove paper by Pennington et al., where they say that they think that log of the word probabilities is some homomorphism of the word vectors. Okay, this is an empirical observation. Levy and Goldberg say that the PMI count of two pairs of words, okay, I should have used WW prime again, is the inner product of the vectors. Okay, chi is just another word, sorry. I should have been consistent in the notation. So the chi is just like W prime. So two words, W and W prime, their PMI value, which is a nonlinear thing, is the inner product of their word vectors. That was a suggestion. So these are empirical, based on empirical models. They don't quite explain the structure, the direction structure. Plus, the error in these observed relationships is too high, and I'll say that a little bit more. So, okay, actually, I'll say that in a few minutes. Okay, so I'll explain this notion of error. The point is that these models indeed sort of fit reality, but there's a lot of error in there, and so you wouldn't expect with that error that there would be such a closed linear structure in the meanings. I'll return to that point. So, okay, let's answer the first question. Why do low-dimensional vectors capture the essence of huge co-occurrence statistics? Okay, and especially with this nonlinearity going on. Okay, so this is empirically true, that you find word embeddings and they sort of seem to capture PMI, and it's been known for many years. And why is this low-dimensional?
If you start with the SVD matrix, then obviously you'll get that, because that's the definition of what SVD.
No. Because if the matrix is not 300-dimensional, it's 100,000-dimensional, so why does it have the low rank approximation? Okay. You see, that's exactly the question I was asking this person, right, this colleague. Like, why? And she said, you measure the singular values and they drop off. But why? Yeah. Was there a question?
I have a question.
Yeah.
So this suggests an interesting possibility if indeed the relationship are the kind of parallel lines.
Not quite, but yeah.
Think about two languages, Hebrew and English.
Yes.
there is no connection between them. Your corpus is either in English or in Hebrew, and you build the three-dimensional structure of each one of the two languages.
Good.
Once you associate 300 words from one language to 300 words from the other language, it looks as if you can get automatic translation of any other word.
Yeah. So that's why I said these lines are not so. There's a two-dimensional projection of the 300. So this is a little misleading. There's a lot of noise still in this.
Attempting to do automatic translation of just aligning the two vector spaces, independent vector spaces.
Okay. So the answer is yes, people are using word embeddings precisely because of those kinds of things, that there is some connection across languages and one-shot learning and so on. But it's much more complicated than that, yeah. But yes, people are leveraging such things. Was there another comment or? Okay, so all right, so why do low-dimensional vectors capture the essence? So what we do is we give a generative model for language with semantics. And a generative model is just a way to, a story, okay, how the data was generated, which seems plausible, and it seems to fit the data. So the suggestion is that, think that there's some abstract discourse space. Say it's in our head, right, or the head of the Wikipedia writers. And there's a discourse space, okay, what's being talked about, and that's low-dimensional. And it turns out it has to be low-dimensional for the picture that I'm going to talk about to even happen. And the discourse vector, there's a discourse vector which indicates what's being talked about at any point in this corpus. And this is this has some semantic meaning, okay? So there's some three-dimensional space where it's pointing has some meaning, okay? The coordinates could have some meaning. Now, each word also has a representation as a vector in this 300-dimensional space. And the assumption is that if the discourse vector at time t is ct, okay, then the probability that a word is output is proportional to the exponential of VW, the inner product of VW and ct. Okay, so it's called a log linear. So we sort of came up with this just thinking about it from first principles, but then we learned that this is the log linear topic model of Knee and Hinton. Okay, so again, the assumption is that there's this conceptual space in our head, or the collective head of Wikipedia writers, where every word has some meaning, okay, where it's pointing. What's being talked about at any point in the document, as there's some discourse vector CT. And the probability when CT is over here, that some word is output, is proportional to the inner product with this direction. So now you see that this has a property that words that have a good probability of being output at CT are sort of, have low inner product with CT. So therefore, they're sort of related to each other. Remember, it's known that similarity corresponds to low inner product. Sorry, high inner product, low angle. So here's an example of, so Yingyu, my postdoc, took an actual paragraph and using our model, inferred the random walk that's generating it. Okay, this is a theory audience. All this showing is that there's a random walk, okay, that you can fit it to the text. Okay, and how it was done, don't ask me, I can tell you offline, how you actually fit the likely random walk to the text. Okay, so there's some conceptual space, and there's this CT vector that's doing a random walk, and as it does a random walk, at every step it emits a word according to this rule. Okay? Any questions? Okay. So that's just, as I said, the Knee and Hinton log linear topic model, but with this random walk. Okay. So now we want to show that in the bulk, this model will have the properties that have been observed. So the key modeling assumption for us, which actually surprises a lot of the linguistic experts, is isotropy, that the set of all word vectors is spatially isotropic. Okay? So isotropic means there's no preferred direction. And we say that in the bulk, they behave like a set of random vectors. So obviously, they are not random vectors, right? Milk and cow are close to each other and so on. But in the bulk, they behave kind of like random vectors. and something like scalar times the standard normal vectors. And the form of isotropy we need is somewhat strong, that for most directions C, this so-called partition function, this sum over all the words of the exponential of the inner product of C and VW is constant. Okay? So if you didn't have the exponential, this is just saying the sum of these vectors is concentrated, which would be much easier. This is the exponential, yeah. Okay, so now we're talking about a generator model. We're assuming there's a ground truth reality, right? And in this reality, each word has is pointing in some direction. That's a ground truth. And the text is being generated out of this ground truth. Okay, so far we haven't observed anything. I'm describing some platonic reality. We'll connect it to the empirical very soon. Any other questions? Okay, so that's an assumption, that these words are spread out in space, so much so that for most directions this is approximately constant. So we came up with this assumption because that's the only way we could make the calculations work. Okay, all the properties that we knew of, they fall out of it, I mean, with some work. And so my postdoc ran the tried to check this isotropy in all the word embeddings that have been computed. And for all the word embeddings that we knew of, it was approximately true. Okay, it's very peaked, this thing.
So in that sense, your ground truth is supposed to model the vectors after they're embedded, not before.
Right. So this is an assumption with a ground truth, and then we are measuring this property on the actual vectors people have found using different methods. And they all have this property. The vectors are not the same, but somehow they have this bulk property. And actually, this is part of a bigger agenda, which I'm not talking about today, that in many settings, machine learning models that you actually find in practice have random-like properties. Obviously, they're not random. They're describing structure in the data. But modulo the fact that they're describing some structure, the rest is kind of random-like. Okay, and that can be leveraged, I think. Yeah?
Relation between the assumption and the generative model of the words?
Okay, so let me now lay out the model again, right? So I've given it in bits and pieces. The assumption is that, so think of the Wikipedia writer as one person. In this person's head, there's an abstract semantic space, this discourse space. Every word has a direction in there. And the corpus is generated by a random walk of this vector CT. And these all possible words, 100,000 words, are sort of distributed in a random way, in the bulk, in his semantic space.
Due to these random walks, right?
Due to?
The random walks in this.
No. Okay. So there are words which are strewn about in this discourse space, randomly, that's this assumption.
According to these assumptions.
Yes, okay. So in the bulk, they look like random vectors. And the corpus is generated by this discourse vector doing a random walk through this space, and as it's at some point, it emits a word according to this distribution. And that's the corpus you're observing. Any other questions? Okay. So this is the way a lot of there's a half of machine learning. So there are different camps of machine learning. This generative models is one large camp of machine learners. Okay. Yeah.
Just to make your life so if I have any collection of points and I do the SVD and I learn that 300 dimensions approximate them, well, then wouldn't I always have this bulk property just because of these orthogonal directions and?
No, I don't see that.
The SVD vectors explain all of the variants, and so they're orthogonal by definition. So you expect this?
No, that's not true. I mean, what you're saying is that any set of 300-dimensional vectors, forget the SVD, any set of 300-dimensional vectors are spatially isotropic. That's just not true.
No, because they could be all on a line. All my vectors can be on one line.
But one line is a subcase of 300 dimensions.
Yeah, but then I will look at the SVD and I will discover that everything is in this line. And so when I look just on the line, it will be...
No. See, think about it, right? So you're saying every set of 300-dimensional vectors, right? So SVD will give you a rank of 300. It's spatially isotropic. That's not true. right? Suppose my ground truth vectors are 3-dimensional. There's no other coordinates, right? 3-dimensional. 3-dimensional vectors don't need to be isotropic necessarily. No, I mean really. I mean it cannot. This cannot be right. 300-dimensional vectors cannot be all isotropic. I mean you can come up with all kinds of 300-dimensional vectors which are not spatially isotropic.
Yeah, but then won't they be also reduce their dimensions?
No, they will be full dimensional. Yeah.
If you look for a fun topic to look at the difference between a corpus which is based on prose and poetry. I believe that in poetry, for example, the model of random walk in which
you
take words which are closely associated with each other is going to be break down. People will talk about red.
Yes, this was already asked earlier that yes, the word embeddings depend on the corpus, on the type of corpus. Yeah, the chemistry corpus will be different from the poetry. Yeah.
Poetry will take words
absolutely.
next to each other which have nothing to do with each other.
Yes. So, okay, so in general, what you're saying is that the distributional hypothesis of meaning has limitations, okay? It doesn't apply to metaphor, which is used in poetry. So let's not get into a lot of philosophical stuff. The surprising thing is that simple stuff works, okay? Not that it explains everything. Okay, so the main theorem. So if you believe all those assumptions, so there's a discourse space, CT is doing a slow random walk, VWs are spatially isotropic. And we have this model that of the words being emitted by the random walk. Then the main theorem is that the log of the joint probabilities is proportional to VW plus VW prime square, the sum of the vector square for the two words. The log of the probability you'll empirically observe will be proportional to the square of the norm. And there's error from log z and plus minus. So this had been observed too, actually. Empirically, some of these things, these correction terms, we used to call them, and they have a certain meaning. Okay, as you can see, z suggests partition function. That's what it is. So the norm of the word vector determines frequency, right over here, how often it occurs, and so this has been also observed. People have seen this in previous word embeddings. They didn't have an explanation. And the spatial orientation determines meaning, which we also know, right? Where they point determines meaning. Things that are pointing in similar directions are similar and so on, because the spatial orientation determines inner product. And then if you remember, well, I've erased the definition of PMI, but PMI was related to these two kinds of things. You do the calculation, it's just the inner product. Okay, so it seems very convenient that everything falls in place. So you try to fit it. Turns out this is not such a good fit, as I mentioned earlier. You know, it's been observed before that it sort of is along there, but there's a fair bit of error in this. Okay, so we found something like 17% term-wise error. This is according to some weighting, so there's some asterisk there, but yeah, roughly 17% error. And this one is a somewhat better fit, 5% error. Okay, so this is just a one slide sketch. So how do you do this? So the probability of what is output is something like this. And so that's just proportionality. So you need the constant of proportionality. That's called a partition function, z sub c sub t. And our isotropy assumption is saying that this thing is constant, okay, for most directions. Okay, and now you can see why the integrals will work out nicely, because the joint probability is, you know, that there was a random walk at c, then it moved to c prime, and then it emitted w and w prime. And this whole mess would be difficult to evaluate, right, to integrate. But the isotropy assumption says that this denominator zc and zc prime are roughly constant. So you take them out of the integral, and then it's a simple integral, then you're home. Okay, that's it. All right, so that's the proof sketch. So it explains previous embedding methods, which were all discriminative. So this famous paper of Mikolov et al. Had the following discriminative model. So there's a difference between discriminative and generator model. This is not a generator model. It's you're fitting to the probabilities, empirical probabilities, but you don't have a generator model for it. Okay, so what you do is you find vectors which fit to this relationship, to the probability of W, given that the other 5 words in the context are W1 through W5. is proportional to the exponential of the inner product of VW times the average vector of these other words. So this is sort of the context, and you're multiplying VW with the average of those. And people have looked at it and said, okay, you know, why average? What's going on? You know, why not something else? Well, turns out the average is just the map estimate, the maximum a posteriori estimate of the discourse vector CP. Okay, and that's how Ying-Yu had produced that graphic I showed of the random walk, fit it to the. There was this expression in the Glove paper, which was a matrix factorization kind of expression. Turns out that's approximately the MLE fit, the maximum likelihood estimate fit for our model. And it gives an explanation to the arbitrary bias terms. I said that people had these correction terms, and there's an explanation. So the expression is something like this. There's some weighting of each term, and you're fitting to this. Okay, that's exactly the Glove model. And of course, you know, we came with the generated model because we knew that these things empirically work, right? So, and Church and Hanks, of course, was the PMI model, which also fits. And yeah, here's the NP-hard problem. This is weighted SVD, and this seems to be NP-hard, but it's solvable in practice. And again, I think because there's a lot of structure. You know, these are not random numbers. I mean, these are not arbitrary numbers, so I think this is solvable in practice. Okay, so that was the generated model. Why do relationships correspond to directions? And the Levy-Goldberg suggestion was that somehow this PMI fact is a reason, but it wasn't quite clear why that leads to directions, because there's 17% noise, and the objective that you have contains 6 inner products. So it's not clear, yeah.
So we didn't actually claim that the directions are explained via PMI. Okay. We explained that the directions are explained, they're not the directions, the analogies are explained because that objective over there, the argument of some x that's close to king minus man plus woman, is actually exactly the same as finding some x which is close to king, close to woman, and far away from man. It's exactly like optimizing these 6 inner products.
Right, but why is it a line? But why is it a line?
It's not necessarily a line.
Ah, so you know,
it's equivalent. So you can look at it as a linear combination of vectors. In this context, when you're looking for one vector that's the nearest neighbor, is actually equivalent to a linear combination of similarities, of inner products.
I think that's a restatement of what I'm asking again, right? Why do these lines arise?
So I'm not sure that the lines exist.
Okay, no, okay, so let's see. Okay, so I'll tell you the explanation. So this was a suggestion in Pennington et al. That what is a relationship, right? The masculine-feminine relationship, which is, we say that they have this relationship is for most words chi, or many words chi. The probability of seeing chi in the context of king divided by the probability of seeing chi in the context of queen is similar to the probability, the corresponding ratio for man is to woman. Because if chi is unrelated to gender, both sides will be 1, right? Whether you're seeing king or queen in the context, it doesn't make a difference to the probability of chi. So both sides will be 1. But if it's not gender neutral, say dress or John, then they deviate from 1 and in the same direction. Bigger than 1 or greater than 1. Or less than 1, yeah.
I have a question about the whole idea of words corresponding to lines. If a word has 2 meanings, it is a kind of linear combination of 2 different directions.
Let's get to the let's put a hole to the 2 meanings. Yeah, that's coming right. Yeah. Okay. Okay. So by the way, you're arguing with things that work. So I mean, this does work. Why it works is a different thing. Yeah. Right, you can't argue that it can't possibly work. Okay, so, all right, so the suggestion was that you find a word W that minimizes this expression. And why log? Because log of 1 is 0. So you take the log of both sides and take the difference square. But if you, so from now on, we'll say this is our semantic notion of relationship, okay? How relationships manifest themselves in word occurrences. So, All right, so the consequence of our model is some kind of a purification effect, that if the relationship is indeed defined in that way, namely like this, that the probability, the log of this probability is just something that depends only on the word in the relationship, not on A and B, plus noise, then you can show that VA minus VB is actually a line plus noise. And this actually, I disagree. I think this is true. We tried many, many relationships, unary, binary, and actually this is more often true than not. And in fact, the noise is very much Gaussian. 1 or 2 dimensional, and the rest is Gaussian. It's indistinguishable from Gaussian. OK, so proof sketch. So actually, that's actually a lot of fun to play with that. See, composers is a one-dimensional subspace, and all this kind of stuff. Beethoven, Mozart. OK, so all right, proof sketch is just so. I think in theory, people don't study linear regression so much, and machine learning is a basic model. But basically, what this is saying is that VA minus VB is a solution to some linear regression with D unknowns and observations. And the point is that the observation matrix, the V chi's, is isotropic. Okay, it's random-like vectors, and then that reduces noise. And that works for fairly general models of noise, also non-Gaussian. Okay, in this relationship, it's a very robust proof. Okay, third thing, polysemy. How does V tie contain the various meanings of tie? Okay, so that's polysemy. And so the thing you would think of is that tie really represents unrelated words. Okay, so what I'm going to describe, this is a new discovery. This was not known. This has been an open problem. What do word vectors, how do they capture different meanings? And so we thought about along exactly these lines and made a prediction using our theory, which turned out to be correct. Okay, so let me show you. So tie represents some unrelated words, tie 1, tie 2, and somehow they've been merged together and given the same name, tie. So the quick experiment is, let's do this. Okay, so take 2 random unrelated words, W1, W2, where W1 is 100 times more frequent than W2, and declare this to be a single word and compute its embedding in our model. So what do you think the word will be? So it's a combination. The title of the talk is Linear Algebraic Structure of Word Meanings. So you'd imagine it's a linear combination, right? Some weighted combination. What would the weights be is the question. So one word is 100 times more frequent than the other. So what do you think? 100 to 1 weights? Sorry?
Same.
100 to 1. Same weights. No, same would be too much. I mean, there are 2 very different words, right? Frequencies are very different. If it was 100 to 1, that would be a very bad representation, right? Because the noise would just swamp out the less frequent meaning, right? You'd never recover the less frequent meaning out of there. So it turns out the result is something more like 0.9 times the first word vector plus 0.2 times the second word vector. This is not exact equality, but approximate equality. And this is mathematically explained in our model, and it turns out this is a logarithm, okay? So according to our model, it's a logarithmic dependence. So now you want to extract different word meanings. So the idea is that these unrelated words that are lying inside tie correspond to different representative discourses. Okay, the discourse vector that was doing the random walk. And so you can turn, and if they are related to different discourses, they have high inner product with those discourses, like the clothing discourse and tying up people or tying up things discourse. So you can do something called sparse coding. Again, this is not very well known in theory, but machine learning people all know about it. So you find 2,000 discourses, A1 through A through 1,000 in 300 dimensions, so that each word vector is expressed as a weighted sum of at most 5 of them. So we're assuming that a word has at most 5 meanings, which, sometimes they have more. But, yeah.
Couldn't you separate those different meanings by looking not at pairwise, but triples of words? So suppose that tie is
Shall I finish and then you can ask questions? How about that? Because I'm out of time. Okay, so empirical fact is that this works. And what does that mean it works? So here are the 2,000 discourses. We call them atoms of discourse. So these are ways in which you can die. So these are visualized using the closest words to the discourse. These are ways in which you can die: social media, horse racing, cell biology, all kinds of very coherent discourses. You call them atoms of discourse. And the 5 atoms that express tie are, the first one is the clothing atom, trousers, blouse, etc. Second is, game, season, teams. Tie is a game. A tied game like scoreless or equal game, scoreline, equalizer, clinching. Tying wires, cables, etc. And the 5th one is jump. Okay, so it got the individual meanings. So yeah, I have now an undergrad using this to construct the automated word net. All right, so conclusions. By the way, this is our project page if you want papers, etc. Conclusion, there's a new generative model for language that directly captures semantics. It ignores word order, okay? So it's not so good on syntax. We're working to fix that. It answers this question, why logarithms, right? This PMI and so on, why logarithms? And the answer is that it allows representation to handle dynamic range, okay? So this word has this rare meaning and a dominant meaning. They're both in there in the representation, okay? And finally, there are other applications of models with random-like parameters. And an ad for this new blog we have off the convex path, which you're welcome to look at. Okay, I'll stop there and take questions. Thank you.
If you wanted to separate the two meanings of tie,
yeah.
You could notice that tie occurs with red, blue, but also with rope and...
So what you're saying is the clustering. That's the way people have done it.
To each other. So you look at all the neighboring words which occur together with tie,
and cluster them.
Notice that they are clustered.
And that's the way people have done it in the past. Okay. Yeah. So people have known how to deal with polysemy. This is answering the question, how does that single word vector capture polysemy? Yeah, people cluster those contexts. Yeah, that's the exemplar approach.